No one tried harder to extend the conventional view of the world than Galileo Galilei. But, as he saw for himself, not everyone sees things in the same light, nor accepts that which is new at first glance. But by 1610, at least to a certain extent, he had a very powerful tool with which to make his argument. Although, contrary to popular opinion, Galileo didn't invent the first practical telescope, he made the most extensive use of it. And at the turn of the 16th century, his simple refracting telescope zoomed astronomy toward the future. As his sketches reveal, Galileo saw Saturn's rings and sunspots, the phases of Venus, the moons of Jupiter, and the craters of the moon. If a man can finally see the large and distant, Galileo must have wondered, why not the very tiny and close at hand? And with a question of that nature, he peered through another invention for which he's given credit. It was the compound microscope, and as his sketch illustrates, with its crude but magnificent power, Galileo was able to see an ordinary Italian bee in extraordinary detail. As he'd done in the science of astronomy, here he had also made an enormous advance in the field of optics. Refraction occurs when light enters a medium, such as glass, and bends. To make use of this phenomenon, makers of glasses, microscopes, and telescopes can grind curved lenses that focus light to a point. A glass prism bends or refracts a beam of light. It also reveals that plain white light is composed of all colors of the rainbow. This process is called dispersion, and it was seen very clearly by Isaac Newton, who investigated both refraction and dispersion. According to Newton, light was made up of particles that, obeying the law of inertia, traveled through empty space in straight lines. Newton explained refraction, or the bending of light by matter, by the gravitational attraction between light and matter. However, at about the same time, and on the same subject, an opposing viewpoint arose in Holland. Christian Huygens, a Dutch physicist and astronomer, theorized that rather than being composed of particles, or corpuscles as Newton called them, light was made up of waves. In the early 1670s, he formulated a principle of light waves, stating that every point on a wave front is a source of new waves. And in 1801, despite the prominence of Newton's rival corpuscular theory, another Englishman, Thomas Young, proved beyond a shadow of a doubt that light is a wave. He accomplished that by proving that light has the wave property called interference. Wave interference can be seen to be constructive or destructive. If the waves, as they travel, encounter each other in step, they can reinforce each other, create a stronger wave, and produce what's known as constructive interference. But when they're out of step, waves can cancel each other completely. In other words, destructive interference. As Thomas Young suspected, all waves in all media behave in this fashion. And to prove that light is a wave, he merely had to illustrate that light exhibits interference, the behavior common to all waves. Here's the principle. Light from a single source enters two slits, which are side by side and not much farther apart than the wavelength of the light itself. After passing through the slits, the light shows up as a distinctive pattern on the screen. When a single plane wave encounters two slits, each slit becomes a source of spreading wave fronts. And because both new waves originate from the same plane wave, their oscillations are synchronized. The result is a stable pattern of up and down ripples, alternating with directions along which the waves cancel one another. This produces a pattern of bright fringes of constructive interference on the screen, separated by dark fringes of destructive interference. And that was it, a series of alternating fringes to prove that light is a wave. It was a conclusive demonstration, and ever since, physicists have had to explain the behavior of light in terms of the properties of waves. Also, a wave's frequency times its wavelength equals its speed. But mechanical waves can be longitudinal or transverse, while electromagnetic waves are always transverse. And in empty space, they always travel at the speed of light. But although they always have the same speed, they can have vastly different frequencies and wavelengths. And in doing so, these waves go so far as to create the entire electromagnetic spectrum. Our eyes are sensitive only to electromagnetic waves having wavelengths in the narrow range from 400 to 700 nanometers. That is, the visible spectrum from violet to red. Even shorter wavelengths, called ultraviolet light, are radiated by the sun. Though these invisible rays are dangerous to living things, they're absorbed and rendered harmless by the ozone in the Earth's atmosphere. Shorter still are X-rays, with wavelengths the size of atoms. And finally, gamma rays, with the shortest wavelengths of all. Gamma rays, with wavelengths as tiny as the atomic nucleus itself, are created by nuclear reactions. Longer wavelengths, extending to visible light and beyond, can be created or absorbed when atoms change from one energy state to another. Beyond visible light, with still longer wavelengths, there's infrared. Infrared radiation can be detected only by the heat it deposits. The universe is suffused with long wavelength radiation, seen as the cool remnants of the Big Bang that started it all. That includes not only infrared radiation, but also microwaves. Microwaves are the first part of the spectrum whose frequency is low enough to be generated by human-made, alternating current electronic circuits. The universe is likewise full of radio waves. Centimeters, meters, or even kilometers in length, radio waves complete the electromagnetic spectrum. Of course, the great Michael Faraday didn't live to see the electromagnetic spectrum. Nevertheless, it began to take shape when, envisioning electric charges surrounded by lines of force, Michael Faraday asked himself a question. What happens when these lines are set into vibration? Faraday didn't quite see the whole answer, but he wouldn't have been surprised by the picture that emerged. An oscillating electric charge creates waves that propagate along the lines of force at the speed of light. These ripples are transverse waves in the electric field, propagating in wave fronts that become flatter and flatter farther from the source, coming more and more to resemble the plane parallel wave fronts that are called plane waves. As the wave fronts pass through each point in space, the electric field vector oscillates up and down, marking the passage of peaks and valleys of the propagating wave. Thus, an oscillating electric charge is indeed the source of outward spreading ripples in the electromagnetic field. It took James Clerk Maxwell's theory to explain the wave nature of light, and to project the image of the electromagnetic spectrum as a whole. Since everything ever seen is the result of light encountering matter, the question is, what is the nature of that encounter? Since all matter is electrical in nature, it all comes down to light waves and electric charges, since light waves are oscillating electric fields. For example, when a light wave encounters an electric charge, the oscillating electric field makes the charge oscillate, which creates a new outgoing wave. A line of electric charges, they might be electrons bound to atoms in a crystal, can produce outgoing plane wave fronts in new directions. And if the charges are free to move easily, as are electrons inside a metal, the result can be to stop the wave from penetrating at all. Instead, the wave is completely reflected. This, once again, is reflection, in which the angle of incidence is equal to the angle of reflection. That's true no matter from what direction the beam arrives. Of course, visible light isn't the only wave in the heavens, nor the only kind of wave that encounters a mirror and bounces back. Just as light waves reflect, so do radio waves. That's why the principle behind radar and the telescope are one and the same. The dish of a radar reflector has the same parabolic shape as a mirror in a telescope. So whether it's the Coast Guard's indispensable radar or the latest design of a 10-meter optical telescope, the object is to detect electromagnetic radiation, following on the same laws and reflecting off similar metal surfaces. No matter the object, from an eye chart at a few meters to an incredibly distant star in the reflecting mirror of a modern telescope, light waves continue to reveal the most amazing sights. And to a certain extent, the journey's just begun.